So what we want to do is we want to come up with a strategy for curve sketching. Now, I'm going to warn you, so this is going to be a general strategy, but because of all the different kinds of functions that are available, things can change pretty quickly depending on what kind of function you have. So it's a good asset to have a general knowledge of the different kinds of functions. But in general, you need three basic things. You need to, very, very importantly, you need to know the domain of the function. This is really important because as you're finding the intervals of increase and decrease, maximums and minimums, if those are outside of your domain, you can be spinning your wheels trying to figure out what's going on. So that's really important to do from the very beginning. The second thing you need is the intervals of increase and decrease. And then once you have those, you can find the maximums and the minimums. And then you also want to find the intervals of concavity. And then once you find that, then you can also find the inflection points. Okay, and then the third thing you need is you need to know where the asymptotes are. Okay. Now, here, the domain, to find the domain of the function, it basically, it depends on the function. So, for example, polynomials have, the domain is all real numbers. But if you have, for example, square root, then you would need to make sure that the square root is greater than or equal to 0. If you have a log, you need to make sure that it's greater than 0, and so on and so forth. So you need to have some knowledge on the function. Now, here, to find the intervals of increase and decrease, and then the maximums and minimums, you're usually going to use the first derivative test. The first derivative test, or if you want, you can use the second derivative test. It's up to you. It's your call. And then to find the intervals of concavity and the inflection points, that you there's no name for it. It doesn't have a test. It's not called the second derivative test. But that's, remember, when you find the pips, and then you find the intervals of concavity and all that stuff that we've done already. Okay, and then to find the asymptotes, remember you have two kinds of asymptotes. Actually, you have three kinds. The first one is horizontal asymptotes. And to find the horizontal asymptotes, remember you find the limit as x goes to infinity. And I'm going to put plus or minus because you have to do both on the positive side and the negative side of your function. Then the other kind of asymptote are vertical asymptotes, and these are, they appear in several different cases. For example, if you have a rational function, when the denominator is equal to 0, you're going to have a vertical asymptote. That's one of the most common ones. And then there are certain functions that have vertical asymptotes. For example, the natural log function has a vertical asymptote at 0. You have tangent that has a vertical asymptote at 0. You have secant, and so on. So these kinds of functions, you have a general idea where they have their vertical asymptotes already, so you can adjust based off of that. And then the third kind of asymptote is kind of a special case. It's the slant or oblique asymptote. And that, remember, generally occurs when you have a rational function and the degree of the numerator is one greater than the denominator. So you basically already know how to do all of this. We've done it before, but we're just going to put it all together. So let's do an example. And we're going to start off with a simple example. Now, it's important to do the domain first, but the asymptotes and the derivative stuff, you can interchange the order of that. Now, for this kind of function, since it's a polynomial, the domain is all real numbers, so you don't have to worry about that. Okay, so then let's do the intervals of increase and decrease. Okay, so to do that, we need to find the derivative, which is 3x squared minus 3. And we'll set it equal to 0. If we move the 3 over and then divide both sides by 3, we get 1. And so then we get that x is equal to plus or minus 1 by getting the derivative of both sides, right? Plus or minus. Okay, so then I'm going to make a little critical point bubble here. So my critical points are x equals 1 and negative 1. And so let's, over here, I'll do my number line. And so we'll plop down negative 1 and 1. And then we pick our test points. So how about we'll do 0, negative 2, and positive 2. So we're going to plug these numbers into the first derivative to figure out whether it's increasing or decreasing. So I'll plug in negative 2 into the derivative. So 3 times negative 2 squared minus 3. This is negative 2 squared is positive 4 times 3 is 12. And 12 minus 3 is 9. So that's positive 9. So that means that my function is increasing here. Okay, and then I'll plug in 0, which is 3 times 0 squared minus 3. And that equals to negative 3. So that means it's negative, which then means that my function is decreasing. So what that means in this case is that I'm going to have since it's increasing and then decreasing, that means that I have a local maximum here at x equals negative 1. And remember, this is the case only if this function is defined at this point. But since this is a polynomial, then it will be. Okay, and then let's do the third one. What color would you guys like? How about this green one? Okay, so I'll plug in 2. This is 3 times 2 squared minus 3. And this is equal to also positive 9, which means it's going to be increasing. Okay, so then that means that this point, x equals to 1, is a local minimum. Now, to find the actual point, remember you need to plug this value into the original function. So we have a local maximum at x equals to x equals negative 1, y equals to, and then if you plug negative 1 into your original function, minus 3 times negative 1 plus 5, this is equal to, this is negative 1 plus 3 plus 5, so this is equal to 7. So that means that my maximum is at the point negative 1 comma 7. Okay, and then the minimum, let's do that one. the local minimum is at x equals to 1, y equals to 1 cubed minus 3 times 1 plus 5, which is going to equal to 1 minus 3 is negative 2 plus 5 is positive 3. So my minimum, let me continue this, is at 1, 3. Okay, so we'll just kind of save those, and we're going to use them to draw our function later. So once we have that, then let's do our concavity. So to find the concavity, remember, you first find the second derivative. And the second derivative is pretty simple in this case. You just get the derivative of this function, which is 6x. And then you set that equal to 0. And that gives us a solution of x equals to 0. So this, remember, we call them pips, possible inflection points, is x equals to 0. How do we figure out if it actually is an inflection point? Well, all we got to do, remember, is you do the number line, and you basically are going to do exactly what we just did for the first derivative test, except with the second derivative. So here's our pip, 0, and we're going to test point on the left and the right of that. So how about negative 1 and positive 1? And we're going to plug these into the second derivative. So the second derivative at negative 1 is 6 times negative 1, which is negative. So this means, because it's negative, that means that it's going to be concave down, or you can write CD. And then when we plug in 1, we get, of course, positive. So that means that it's going to be concave up. Okay, so that means that this point right here is going to be an inflection point because it changes concavity. Now, what is the actual inflection point? Well, it's when x is equal to 0 and y is equal to, take a guess. Of course, you're going to plug it into the original, just like for the maximum and the minimum. So x is equal to 0, y is equal to 0 cubed minus 3 times 0 plus 5. Well, this one's easy. That equals to 5. So that means that my inflection point is at 0, 5. So this is where it goes from concave down to concave up. Okay, so we have all of this information that we just found. And then before we graph it, let me just sort of state the asymptotes. You don't have any asymptotes here because this is a polynomial. So you already know right away that you're not going to have any asymptotes. So you don't really have to do anything. You could try finding the limit as x goes to infinity, but it doesn't make any sense to do that in this case. So let's put down our information over here and then graph the function. Okay, so I've summarized the information that we found right here. I said that our function is increasing from negative infinity to negative 1, and then again from 1 to infinity, and it's decreasing from negative 1 to 1. That's what I got from my intervals of increase and decrease. A question that I get asked a lot is, how come these are parentheses? How come they're not included even though our function is defined at negative 1 and 1? The reason why is because what you're stating here is that it's increasing on this interval, and exactly at the point negative 1, remember that's a maximum, so it's neither increasing nor decreasing. That's why these intervals have parentheses, but that doesn't mean that your function is not defined there. It just means that it's not increasing or decreasing. So I just kind of wanted to point that out. Okay, so let's do a rough sketch here. Let's say this is -1, and let's say this is +1. And we know we have a max at -1, 7. So at -1, 7, let's just say 7 is right here. Here I'm going to have a maximum, so it's going to look kind of like that. And then at 1, 3, I have a minimum. So let's just say that 3 is right here. So since I have a minimum, it's going to look, something like that. Again, this is a rough sketch. Okay, and then at 0, 5, I have an inflection point. So right around here, my function is going to change from being concave down, which is what it says right here, to concave up. So if I take all of this information, that's enough to draw the picture relatively easily, because I know that it's increasing from -infinity to -1. So it's just coming down, and it's concave down. Okay, so at -1, then it starts decreasing, and it decreases up until this point. It's decreasing concave down, but then at this point, it becomes concave up. Now, it's hard to see exactly where that happens, but we're just going to assume that it's right there. It becomes concave up, still decreasing, and then at 1, it starts increasing, concave up still, and it increases all the way to infinity. So that's what our function looks like. So again, this is a simple example, and I went through it pretty slowly, but we're going to go through several more examples, getting progressively more difficult.